Can everyone see this?
Yeah.
Yes, sir.
All right, thanks. So yeah, before we get into things here, I'm just going to lay out what topics I want to cover today. So we're going to start with a crash course on pointers. Hopefully a lot of this stuff should be old hat for you. If you've never worked with raw pointers before in Rust, then I'll be covering a little bit of how to work with them here as well. So maybe if you're only used to working with Rust's safe references, then you might learn a little bit new here. But other than that, we'll be talking about what pinning actually is, how the pin type and the unpin trait work, and then we'll get into some of the motivations for why pinning is important. So like I said earlier, this talk is kind of aimed at people who have some experience with Rust. So maybe you've read through the book, you understand how generics work, and you're familiar with traits, you're comfortable working with them. And I think I don't think that I have much else required there. I guess understanding references and the borrow checker definitely helps. But otherwise, yeah, not too much else should be required. We will be also kind of diving a little bit into async, but hopefully you shouldn't have to really understand anything about async to understand that part. So yeah, we'll save that for the end though. So for our crash course on pointers, of course, I'm going to start with memory. So I think I heard the hand raise sound or something. I'll check.
It was the chat.
Okay, it was the chat. Okay, I'll be checking for questions at the end, and then we can come back and go over anything that might be confusing later. But anyway, so yeah, here's sort of what memory kind of looks like at a high level. Sort of an abstract representation here is just consists of addresses, and at every address there's like a value that you can store there. So for instance, if we do something like let I equals 4 in Rust, and create some kind of integer here, that might store this value like 0x4 here at this address, 0x1000. And if we want to create a pointer, we can use those little ampersand here. And it's similar to C, and basically a pointer is just a value that happens to be the address of another value. So you can see that this value here is 0x1000, which is the address of this integer that we defined earlier. Now I didn't define any types here, but yeah, there's a variety of different pointer types that are available in Rust. So here's not an exhaustive list of pointer types in Rust, but kind of the more common ones that you'll see. So in the raw pointers section, we've got star const t. So this is like a read-only pointer. We have star mute t, and this is a mutable pointer. So raw pointers in Rust generally not really safe to work with. You can create raw pointers just fine, but in general, if you need to dereference a pointer, you have to use unsafe for that. We'll talk about that in a second as well. Next, we have our regular references. So these are like the shared references and the exclusive references that you're probably familiar with. If you've written a lot of Rust, you see these all the time. And these are, very, very, very common. They're safe, they're checked by the borrow checker, and you don't really need to worry about using unsafe or anything like that to work with these for the most part. So yeah, the shared references can be safely shared. And of course, the exclusive references, you can mutate the value behind them. And so you can only have like one mutable reference at a time. Lastly, I want to talk a little bit about smart pointers. There's a lot of different smart pointers in Rust, but the most important ones, the most important one for this talk to understand is just box. So box is like C++'s unique pointer, and it basically just says, hey, if you want to allocate some object on the heap, you can, put it in a box, and that object will live until basically the box pointer goes out of scope and then is deallocated. So it's just a safe way of allocating objects on the heap. We also have like RC, which is for like reference counting, and of course there's like arc, et cetera, et cetera, et cetera. But I'm not going to get into that because the only one that you really need to know for today is box. So for those who haven't worked with raw pointers before, here's a little bit of syntax to try and help you understand and get a little bit familiar with it. So here I have I have a pointer to an I32, this 32-bit signed integer, and it's a mutable pointer, which is why it's star mute. And we can create a pointer of this type using ampersand mute. If we were to use star const instead and create a read-only pointer, it would just be ampersand. And so it's very similar. It's analogous to your regular shared and exclusive references. So next we have a pointer dereference. So if we want to create a variable y with the type I32, we can just dereference the pointer using the usual dereferencing syntax here with the star in front of the variable name. However, of course, these are raw pointers, and so in Rust, you actually have to make sure that you're using unsafe if you want to do this. And same here if we want to mutate the pointer. So this is only possible because we have a star mute. If this was star const, we would not be able to do this. But in this case, here we're just using the pointer dereference to be able to mutate what's behind the pointer and set the value to 3. And of course, that also requires unsafe. So just to quickly recap here, unsafe is a keyword that just allows you to do these 5 things here. We're only really focused on 2 of them for today, just being able to dereference raw pointers and call unsafe functions or methods. Those are the only 2 things that we'll be utilizing today. As usual, unsafe doesn't necessarily mean that your code is unsafe, right? It just means that the compiler can't verify that this code is actually, not going to trigger undefined behavior. It's kind of up to you to, verify that the code is doing the right thing. It's sort of like a trust me. So, yeah, just in case you're confused and you see unsafe, you think, oh my god, that that does something unsafe. No, they wouldn't add a construct that just makes your code automatically unsafe. So yeah, with all that out of the way, now we can talk about what pinning actually is. So pinning is a term that refers to the placement of objects in memory and trying to make sure that those objects aren't able to be moved. So in other words, we're just trying to pin data to a particular location in memory. And in particular, this actually really only seems to be useful when working with self-referential data. I haven't really seen any other use cases for pinning. There might be some out there, but largely all the context that you'll see pinning used in is with self-referential data. So what do I mean by self-referential data? So imagine we have this struct foo. So foo has 2 fields here. It has a field A, which is a U size, and it has a pointer, which is a read-only pointer to a U size. Now, the Rust type system isn't strong enough to be able to say that this pointer specifically points to this field. Like the name suggests, it's a pointer to A, but there's no way we can actually express that in the actual type system itself. So just something to keep in mind. So in our example here, we're going to create two foos here. We have foo1 and foo2. And we're going to set their fields to the corresponding values here. So we've got a equal to 0. And in this case, a pointer is going to point to foo1.a. So this is a self-referential struct, right? Foo1 has a pointer to itself. And same here with foo2, but instead of a 0, we're going to set a to 1. And so what do you think will happen if we try to use mem swap on it? Well, this is what actually happens if we try to swap the values around. So when you call mem swap on these two foos, what's going to happen is all the values that were in foo1 get put in foo2, and all the values in foo2 are put in foo1. We can kind of see that here. Like there's a 0 here, and 0x1000 here, and then we see that that ends up down here. So when we look at the values here, we see that a equals 1 so far so good, but we look at the value here and we realize that, hey, wait, this address that this pointer is using is actually pointing at the other struct now, and vice versa. Foo2 now has a pointer back to foo1. And if we wanted these structs to just be self-referential, then swapping these two in memory has now caused a bit of a problem, because now we have pointers pointing in the wrong places. So this is sort of the main problem that pinning tries to fix. Is it says, hey, if we can just pin the placement of these pointers, and we don't really have to worry about stuff like this happening and everything going all wrong with the pointers pointing in all the wrong places. We can make sure the pointers aren't invalidated in any way. So just to show what that looks like in code, I kind of threw together a little playground example here. So for those who are not familiar with the Rust playground, you can just go to play.rustslang.org here, and you can kind of just mess around with Rust online, and then like an online editor. I have Vim key bindings turned on, but you can there's other key bindings as well that you can choose from in the configuration. Anyway, here I've defined foo. I added a debug for it so that we can easily print it later. And yeah, it's defined as I showed earlier. It has a of type usize and a pointer, which is a read-only pointer to a usize. And down here, we're creating our two structs, foo1 and foo2. Notice that here I'm using a null pointer. That's because foo1 doesn't exist yet, so it's kind of hard to create a pointer to foo1 when chicken and egg problem, right? So we set this to null first, and then same for foo2, and then we set the pointers later down here. And yeah, after that, we just we do the mem swap between the two. And here I'm printing out some values before and after the swap, so we can take a look at those here. So yeah, we see that foo1 has a 0, and it has this address for a pointer, and the value pointed to by that address is 0. And when we see after the swap, we see that it's a 1 and has a different address here, and it's still pointing to 0. So yeah, this is pointing to this struct a field now, which is what we don't really want. And what else do I want to note? Of course, we have to use unsafe here if we want to actually print the value pointed to here, because we're dereferencing the a pointer in foo1 and foo2. But yeah, there's nothing really special about that otherwise. So let's go back. All right, so now we can talk about how do we accomplish pinning. So there are two types that are used quite often when you're working with, when you're trying to pin data. And well, actually, I guess one isn't technically a type, but we have one type and one trait. So we have the pin type and we have the unpin trait. So what is pin? Well, pin is actually just a wrapper around a kind of pointer that makes the pointer pin its value in place. So it basically just prevents the value pointed to by your pointer P from being moved in memory. So P, you can imagine it being like a star const I32 or like an ampersand mute I32 or whatever. And yeah, it'll try and pin that in place, but we also have this unpin trait here. So this is a definition of the unpin trait. It's rather small. There isn't much to it because it's actually just a marker trait. So it's actually an empty trait. But there is one thing that I want to point out here, in that it's an auto trait. So what are auto traits? Well, auto traits are just traits that are automatically implemented for all types. So if you want to actually not implement unpin, you have to explicitly opt out of it using a negative impl. And now negative impls, I believe, are an unstable feature. So you won't be able to do that on stable Rust. But there's a way around that. So if we want to opt out of the unpin impl, well, I'll get to that I'll get to that in a second. There is a way to do that. But basically, the way that unpin works is that it removes the restriction of pinning on a type. So, for example, if I try to create a pin ampersand mute I32, as we see down here, if I32 implements unpin, which it does, then pin actually has no effect on it. So you can still move this value around freely in memory. So it kind of makes sense. I mean, given the name unpin, it kind of just cancels out the effect of pin. And for non-pinned data, this has no effect. Kind of obvious, but you know, since it's implemented for everything, yeah, and you probably haven't ever noticed its effect on your day-to-day coding. Yeah, I feel like that doesn't really need to be explicitly said, but I just wanted to point that out. So if we want to actually not implement unpin for a type, the way we do that is with something called phantom pinned. And phantom pin is just a marker type. So any type that contains phantom pinned will not implement unpin. So this is how you use this is how you implement not unpin, I guess, on stable Rust. Or I guess they usually say you're not implementing unpin. And the thing about marker types is that in Rust, marker types are zero size types, so they have zero overhead. They don't take up any space in memory. So they're 0 bits essentially, which means that they're free. They exist purely for the compiler to use for like static analysis, which is nice. So yeah, with all that out of the way, I kind of want to just dive into a bit of code here, showing how pin and unpin interact, because that's kind of a lot to take in. And it's kind of hard to really understand how pin works from those descriptions alone. So I kind of threw together this this playground that sort of experiments a bit with pin and unpin and phantom pinned, and kind of shows how they interact together. And yeah, so first I want to go over the struct definitions here. So we have a struct foo. It's an empty struct. So this is basically just like a singleton type. You can construct a foo, and foo is the only value of that type foo. And yeah, that's that's pretty much all you can do with it. It's nothing special. However, because like I said earlier, unpin is an auto trait, foo will automatically implement unpin, so there's no need to do any kind of derive. And here we have another struct called bar, and bar does not implement unpin, and the reason for that is, like I said earlier, if you have this phantom pinned in your struct, then it will basically do the negative impl for unpin for you. And yeah, once again, this field is a marker field, so they use the underscore here to indicate that it's an unused field, and it purely exists for the compiler's sake and doesn't actually take up any space in memory. So let's dive into main here. So I create two foos. The first one is mutable, the second one isn't. And for our first example, I create a pinned mutable reference to foo1, and that's called foo1 pinned. And here I call memory place. So what memory place does is it just replaces the value pointed to by this first argument with the second argument. So it's going to replace foo1 with foo2. And this is allowed. And that's because foo, of course, implements unpin, right? So we're moving the value pointed to by foo1 pinned, even though it is, it is pin. Because foo implements unpin, that cancels out, and so this is actually allowed. So down here we have two bars, and these both have phantom pinned, of course. And in this case, this is actually not allowed. So we're gonna. I was actually gonna try and do this standard memory place here, but I couldn't even get that far because, as you can see here, when I try to compile the code, it says phantom pinned cannot be unpinned, and I thought this is kind of interesting. So the reason for this is because pin new, this constructor for pin here actually requires that t, this type here, that's being pointed to, that the target of this pointer type here is actually unpin. So it feels a little bit counterintuitive just reading the types. You're like, okay, I want to like pin this thing, but what do I have to pass in? Oh, I need to pass in something that actually implements unpin. So that was a little bit of a surprise for me, but yeah, that's how this API works. If you want to just create like a pin new like this, you have to make sure that this thing actually implements unpin. And so as expected, if you change the type of pointer, so if I use a box smart pointer instead, that doesn't change anything. So if I compile this, same error. However, this one feels a little bit magical. So it basically does the same thing as the one above. It tries to create a pinned box pointer to a bar. However, this one actually does work. So we can compile this and everything's fine. And when I saw this the first time, I was very surprised. I was like, why does this work and this doesn't? And it turns out it's because they actually use unsafe under the hood. So we can actually like look at this code here and see that, yeah, right here it uses unsafe, pin, new unchecked, and that's why it's able to create it. But it wraps it up nicely in this safe API. So if we want to use box pin ourselves, we don't have to use unsafe explicitly in our code. So that's nice. So for the next example here, I tried replacing bar 1 pinned with bar 2. And that doesn't work. And the reason for this one is a little bit tricky. So it says that the trait deref mute is required to modify through a dereference. So this dereference is not okay. this one here. But that's not implemented for pin box bar. So the reason why that is because dref mute is not implemented for pin box bar unless bar implements unpin. So that's something that we can more easily visualize if we look at the source code for that. So we can look at the impl for dref mute, right? If you don't know what dref mute is, it basically allows you to use the dereference syntax for a type. So you can define your own like pointers by implementing like dref or dref mute for your pointer type. So here they're implementing it for pin because it's a wrapper for a pointer. But yeah, you'll notice that target has to implement unpin for that to work. So I thought that was kind of interesting. But it kind of makes sense logically. If you don't think too much about the types, if you're not like looking at the types directly, it makes sense that you shouldn't be able to do this because you've pinned this thing, right? This bar is not unpin. So now that we have a pin to something that isn't implementing unpin, of course, if we try to move the value behind that pointer, in some way by doing like a memory place or a mem swap, of course that shouldn't work logically, right? Because then that violates the the pinning contract, right? So for the last little example here, I went back to creating foos. So once again, we're back in unpin land, and I did the box pin again but for foos instead. And yeah, we can see that here it actually does work to do the replace, and that's because foo implements unpin. So everything's okay, and dref mute is allowed to be implemented for this, and we don't run into any issues. So hopefully that kind of gives you sort of an intuition for working with pin and unpin. It's a little bit weird because just looking at the types, it's kind of hard to understand what's going on. I find it not exactly super readable, but when you actually like think about it logically, like what does it mean to pin data? It means like keep it in a certain location in memory and not move it, right? Then when you see what operations work and which ones don't, you kind of realize, aha, like that's of course this wouldn't be allowed, but this one wouldn't be allowed. Like this is unpin, so of course like why I should be able to just move something that's unpin. This is not unpin. I shouldn't be able to move something that is not unpinned because it's pinned. But yeah, I don't know, maybe not the best explanation in the world. It is still pretty complicated. I definitely recommend checking out the docs for pin. But yeah, hopefully that gives you at least a little bit of intuition for how it works. So with that, I'm just going to jump into the motivations for pinning. So why is pinning important? Well, like I talked about earlier, it's used primarily for self-referential data structures. So there are some that just kind of naturally occur, like this intrusive doubly linked list that they talk about in the documentation for the pin module. So that's just a data structure that just happens to have self-references naturally. So it makes sense that pinning would be used there. But where I see pinning used the most is in asynchronous code. And so the reason why async code ends up using pin a lot is because the async await syntax in Rust generates these state machines under the hood when you compile your code. And those state machines, when you generate these state machines, you also generate some types with them. And those types, they sometimes use self-references under the hood. Not always. There are certain cases where they don't, but I'm going to just show you what I mean by just going to the book, because I think the book explains this really well. So this is the Rust async book. There's an entire section dedicated to pinning here. I would also recommend checking this out if you're interested. But yeah, here's the example that I wanted to go over is, so here we have an async await block here. So we have async, and we await two futures here, future 1, future 2. And when you compile this code, it'll actually generate this async future type. for the async block itself. And that async future will have a state. So that state will be either awaiting future 1, awaiting future 2, or we're done. And of course, it also holds on to the two futures themselves. And down here in poll, we can see already from the signature of poll, like when we implement, whenever you implement future for any type, the signature for poll already will always take a pinned mutable reference to self. So you can already kind of see where things are kind of heading, but in this particular case, that's not really relevant. What this code is just doing is it just checks what state we're in, right? And then if it says we're awaiting future 1, then it pulls the first future, it gets the result there. If it's pending, then we say that we're pending. And if it's ready, then we set the state to awaiting the next future. Same thing here with the second future. If that one's done and it returns a result, then we just set the state to done. And then if we're done, then of course we just say we're ready. So yeah, that's kind of how async await just compiles down to state machines, but obviously that hasn't really involved pinning yet. So here's kind of where pin gets involved, is when you have async blocks that use references. So here they create an array called x, and they pass a mutable reference to x to this read into buff function, which returns a future. So it's an asynchronous function. And they await it, and then they print x here. And what you'll notice is that when compiled, when it creates the async future type, which again represents this entire async block, it stores x as a field here, right? That's this array here, and it also stores the future, right? And it stores it as read into buff, but read into buff has a mutable reference to an array or an array slice, and that actually is pointing to this x field here. So essentially, async future contains a struct that has a reference to async future's other field, which creates a self-reference. So this is why pinning starts to get involved. And it's a pretty common case, right? Like you expect to be working with references all the time in Rust. So adding async to the mix shouldn't really change anything. So of course you're going to be using references in async Rust, which naturally means that you're going to be running into this case quite often. So I thought that was just like a really good way of kind of motivating why it's important to understand pinning, at least with respect to async, because that seems like by far the most common case for pinning. And before we end things off here, I just wanted to go over a slightly more concrete example of using pin. So this example is actually based off of this blog post's example, this Cloudflare blog post. I made some minor modifications to it, but essentially what we're doing here in this example is we're trying to create a wrapper for a future that times that future. So we have this timed wrapper, and essentially when you await a timed future, it'll return the result, but it'll also return the time elapsed, so you can measure how long it took to run that future. So in this case, we have a future foo, or well, this foo function returns a future. It's an empty asynchronous function, but you can imagine that this might be something like, I don't know, read from socket, for example, or like read from buffer. Like any kind of asynchronous computation could go here, and you could try to time it using this timed type. And yeah, once we get the result back and the elapsed time, we just print the time that elapsed. So if I run this, this was working literally yesterday. Okay, interesting. All right. Well, never mind. It was working yesterday. I don't know why that's not working now. For reference,
Does it have to run on unstable? You have it on stable set.
it shouldn't. It was working on stable yesterday when I ran this. Yeah. I guess pin project isn't popular enough anymore, and it fell out. I don't know. The way that the playground works is it pulls in, I think, like the top 100 most popular crates, and then you can use them as dependencies. But yeah, pin project was working just yesterday when I tested this, but maybe that list got updated, and now that's no longer the case. But anyway, I guess just pretend that it worked. All it did was it printed the time for that computation. That kind of sucks. Oh well. But yeah, so I pulled in some third-party dependencies here, as I mentioned. So here I'm using Tokyo main because we need some kind of runtime to execute our asynchronous code. And so I decided to just go with the Tokyo runtime because I don't know, why not? The other dependency that I pulled in here was a pin project. So pin project essentially allows you to define safe pin projections, as we can see here. If I look at look at this project, yeah, create for safe and ergonomic pin projections. But I haven't really talked about pin projections. What are pin projections? Oops, wrong tab. So if you actually look in the documentation for the pin module, there's a subsection here that talks about projections and structural pinning. So whenever you're working with a pin struct, you might have to access the fields of that struct. And so there's basically two choices for how that can work. You can return a pinned reference to the field, or you can return just like a regular reference to the field. And it's basically just up to the author of the data structure to decide whether or not to return the pinned field or just the reference to the field. And basically, if you return the pinned field, that's called structural pinning. And if you don't, then it's not structural. So if we want to expose these projections, we actually have to use unsafe here. And then there's a bunch of rules that you have to follow. They outline a bunch here for when pinning is structural for field. But yeah, well, the whole point of pin project, this crate here, is to make sure that you don't actually have to write any of that unsafe code. It wraps it up in a nice safe abstraction. So yeah, it's just a nicer way of generating these projections without having to actually touch unsafe ourselves. So with all that out of the way, let's get into the definition of timed. So timed is just a wrapper for a future f. This is just a generic type argument. The reason why I don't do something like this is, and the blog post itself actually does this, but I generally consider this to be a bad practice, and I know some Haskell developers do as well. The reason for that is because once you start trying to pass around a timed a timed future or whatever, you're going to have to require every function that calls or that uses time to explicitly declare that the type argument implements future, and that kind of like it becomes very pervasive, and it's pretty annoying. So it's generally considered better practice not to put your trait constraints in your actual type definitions. So we have another field here as well. We have start. So this is just the start time. It's an option of an instant because we have to initialize it as none to begin with. And you'll notice that for future, we use pin here. This is just creating the projection, which we will talk about a little bit more later. Down here, we have the constructor for timed. So normally this is the one that would be, this is the one that would be pub if we were to expose this in like a library or something, instead of, the default constructor for the struct. And yeah, we just set start to none, and we just take a future and set future to that future. Now we get to the actual future impl for timed. So here is where you would put the trait bound on F, and this is a bit more flexible. So the output here, like I showed earlier, is just a tuple. It's going to be whatever the output of this future is, and a duration. That's the time elapsed that we saw earlier when I was going through main. And I actually have two different implementations of poll here. I'm going to show the first implementation here, sort of like what you might do as like a naive approach, right? If you're not that familiar with pinning. So the naive approach would be to do something like this. You call get or insert with to get the starting time using instant now. So this sets the time. This starts the timer. We call self.future to get the wrapped future and poll it. So we want to get the result of that. And then here we get the elapsed time by just calling start.elapsed. And so depending on the state of that polled future, we either return pending if it was pending, or we return the result with the elapsed time. And you would think that this would be just fine, except, okay, let me just get rid of this so I can demonstrate my example a little bit better. Sorry, this is very unexpected, but it's not the worst thing in the world. We can work around it. So here we see that poll is actually not defined for self.future, and that's a little bit confusing. It says help, consider pinning the expression. So that already kind of gives us a bit of a hint here. But essentially, as the comment here kind of spoils, when you're implementing the future trait for a type, the poll method requires that self be a pinned mutable reference to self here. And in this case, self.future is not pinned, right? We can see from the type here, it's just not, there's no pin involved there. And so it fails to meet the requirements for the future impl, and we can't call poll on this future. So the solution would have been, if the dependency worked, to just add a projection, a pin projection there. And here we basically just add this line self.project, and we go this.future.asmute.poll, and this would have worked. This would have worked if it weren't for the issue with the third-party dependency, but oh well. I probably could have just written out the projection manually, and that would have been fine, but oh well. So yeah, here's kind of a case where you kind of need to be aware of pinning in order to make your asynchronous code work. And I feel like this is sort of a more practical use case as well, because like timing an asynchronous computation is something that you might actually want to do, right? So you might actually try and define this wrapper yourself and run into these issues. So I just wanted to try and give some more motivation for why you might want to understand pinning a bit better. But anyway, that's pretty much it. I don't really have anything else. I have some further reading here. If you want, you can look at the pin module documentation. It has a lot more details there. Again, there's the pinning section in the async book. At the bottom of that page is actually a nice summary of the rules of pinning here. I recommend giving that a read through. And yeah, lastly, once again, this is the Cloudflare blog post that I based my example off of, in case you want to see the original. But yeah, that's pretty much it. So do we have any questions or comments?
Could you post the links in chat so that we can take a look at those?
Sure. Yeah, I can post some of the links in chat. I'll just post the ones from the further reading.
Thank you.
All the links will be posted later. Someone already posted the pinning section there. Thank you.
Okay, okay.
And yeah, all the slides will be uploaded later to our repository. So you'll be able to check it out later if you want to check out the playground links and mess with it yourself. That's fine as well. Whoops, I copied the same link twice. All right, there we go. That should be everything. Thank you, thank you, thank you.
So, Jonathan, yeah, thanks. That was a great presentation. I had a quick question just from the examples that you had for the pinned objects, even in the self-referential case, it looked like you were using like pin new or pin, which I guess means that you have the objects already created in this stack and then it's getting moved to this like pinned location. So I guess it was box pin. So does that mean that like you have to make your pinned object with like box pin and then set whatever your self-referential data is?
Yeah, pretty much anytime you want to create a self-reference like that, you have to create some kind of like null pointer or something first and then set the pointer afterwards to do the self-reference. The example that they use in like the pin module documentation, I think they use like non-null just to ensure that that pointer does get initialized later. Like they use like pointer dangling to begin with, but it's essentially the same thing as using the raw pointer, just a little bit safer. But yeah, you pretty much if you're working with pin like this at this kind of like raw level, you're gonna have to use unsafe, almost guaranteed. So that's kind of why unsafe kind of played such a big role in this talk. I was a bit surprised at how much unsafe was required, but like as far as I can tell from my experiments, like if you try to create like a pin wrapper around anything, like like you see the definition for pin new, it requires that the argument is unpinned. So if it requires that the argument is unpinned, basically pin will never affect anything, right? Because it gets canceled out by unpin. So the way that I see it is that the only way to get pin to actually have an effect is to use something like that unsafe uh, uh, get unchecked or whatever, like what they use for box pin. And then you can actually pin something that doesn't implement unpinned. Like you have to use unsafe to kind of like work around that. And that's kind of how they, I guess, filter out like what should be allowed or what values are pinned and which ones aren't through the type system. It's a little bit of trickery. They kind of hack around it using unsafe, I guess. Maybe not a hack, but like they have to use unsafe in order to like allow certain values in and then put that in a safe API so that you can just call something like box pin from your safe Rust code and not have to worry about reaching for unsafe yourself. But at some level, unsafe is pretty much always going to be involved, whether it's in your code or it's in like the library code. Like when we looked at pin project, there was a bunch of unsafe code there.
Oh, okay, thanks.
Yeah, box pin is sugar for pin box T, but you can't actually do a pin new box new T. You have to use box pin because it uses unsafe under the hood. Do we have any other questions or comments, concerns? Momori?
Yeah, thank you for presentation. And I have a question. So, is pin necessary only for pointing references protected by Rust compiler? So it's impossible to move value that is different by another variable, but a pointer doesn't guarantee such rule. So that's the reason why pin is required. So is it correct?
There's a part where you cut out for a second, so I didn't quite catch the whole thing. But I'll try to answer what I understood from that. Pin is so pin like I showed in the earlier example with the two foos being swapped around. Pin basically says that the value pointed to by a pointer doesn't move in memory. That's what pin is for. It's to make sure that that value never moves.
Mm-hmm.
So you can't do the swap. You will never be able to call that. The code will just fail to compile, and it would say nope, that swap is not allowed.
Mm-hmm.
Does that make sense?
Yeah. Okay. So and we don't have to use pin when we use reference, right?
Oh, like regular
Yeah,
shared
regular
references?
reference.
Yes.
Not pointer.
I believe so. I don't know how it interacts with interior mutability, like with refcell, for example. Like if you have like a mutable or like a shared reference there, like you can use interior mutability to still mutate behind a shared reference, but otherwise, like there's a reason why I didn't show that. Is like the common case is you're usually working with mutable references, or you're usually using it with box. Anything where you might actually be able to mutate the value behind the pointer.
Yeah. Okay. Thank you.
Yeah, you can also try it out in the playground if you want. Like you can create like a pin, just regular shared reference to like an I32 or something that like bar that doesn't implement unpin, and try doing like the mem swaps, and you'll probably see that it's you're just not allowed to do the mem swap at all because it's immutable. Good question.
Thank you.
Anybody else? Any questions? Comments? Concerns? I do have a couple of other things I need to talk about today, so I might try and hurry things along here. Going once, going twice. All right. So first things first, I want to talk very quickly about the API World partnership that we've got going on. So I think that event is happening pretty soon, just a little bit later this month. And I know some people have already signed up for it, but for those who are intending to sign up, please remember to sign up using the link provided. And that's all I wanted to say about that. Thank you to those who did actually sign up. It's anonymous. I don't actually know who signed up. I know that some people did. So thank you. Other than that, updates on the office. So physical venue still pending. The last update I got in the office was that honestly they don't know what's going on, but they know that carpeting has been installed. So they're making progress. I don't know when they'll have like furniture and everything moved in and set up, but yeah, I think the last update was they promised, like, or I guess they didn't promise. They said like they were estimating around mid-October. Well, it's mid-October now, and yeah, I just thought it'd be appropriate to give an update, and let everyone know that it's continue to be patient. I don't know when this will be done. They keep pushing back the date. It's annoying. It is what it is though. So yeah. But yeah, with that, I don't have anything else that I want to talk about. So if anyone wants to talk about something, we still have a little bit of time left. if you have any questions about Rust in general or just any topics you wanted to discuss, now's the time.
There was a question in the chat asking if we'll be using the office for in-person events.
Yes, the office will be used for in-person events. Yeah. So in the future, in the shiny future, we will be able to have in-person events where people who can attend in person will be allowed to come into the office and hang out physically. And for those who can't attend, you can still join virtually. We'll try and make sure that accommodations are good for you as well. I mean, Chester here will, he lives in Toronto, so basically, yeah, I want to make sure that he still has a good experience, and so I'll make sure that everyone here who can only join virtually is well taken care of still. Anyone else? I also wanted to mention really quickly, like if you feel like you want to do a talk yourself here, like you can go ahead and ping me or ping Chester, and we can slot you in. I like to do these talks personally because it helps me learn new things. Like the whole motivation for this presentation was for me to learn more about PIN and share some of the experiments that I did with PIN and how I learned about it. And I find teaching is one of the best ways of learning things because you kind of really want to know what you're talking about before you present it to someone else. So if you ever feel like, you want to learn something new and you want to come and do a talk, yeah, go ahead and just let me know or let Chester know, and we can help schedule you in. Yeah, no problem, Azam. We'll keep the streaming option available. I'll make sure of that.
Actually, I have a question. Thinking of doing a talk in December, and I wanted to know which one people found more interesting. I'm planning to Advent of Code this year in Rust. So I was saying one of the options I could probably do is present on what I learned about Rust doing Advent of Code, because I do lead code in Rust and I learn things about Rust because they ask questions that are not very Rust friendly. So they'll ask questions about linked list and those kind of things. And I learned that easy questions in Python are sometimes challenging in Rust because of the pointer management. Borrow checker management in terms of what can be created when and what has a pointer to what. The other thing I thought that might have to be interesting as well is I had to do a project for my thesis where I had to build a program in eGUI. Well, I didn't have to do it in eGUI, but I chose to do it in eGUI, and that's kind of cool as well. So if you guys want to see a project that's developed in immediate mode GUI in Rust, that's another option. I was just kind of curious which one people thought would be more interesting.
Both.
Both. Well, I don't want to do too much of a long presentation, but yeah, I could try to do both. So
But
that's
they're
an option.
personally they sound really interesting topics. So whatever comes first, it's fine for me. But they sound really interesting, really.
Okay.
How about you do 2 presentations? They don't have to be like one after another, but you can do one for December and then save the other for another time.
Okay. Well, I can do Advent of Code in December, I guess, because it'd be topical, and
Yeah.
I'll do the eGUI one another
Just
time.
the season.
Just the season.
Yeah.
Sounds great.
Okay, sounds like a plan. Thanks.
All right. Any other last minute questions or comments before we break off here? Going once. Going twice. All right. Cool. Thank you all for coming. Oh, I heard myself.
Jonathan, that was really great.
Yeah, no problem. Yeah, thank you all for coming. I really appreciate you all coming out here tonight. This was a longer presentation, but hopefully you got something out of it and it was useful to you in some way. Even if you don't understand PIN, maybe it helped you understand a little bit more about like what Rust is all about. And yeah, hoping to see you all next time. The plan for next time is to do another talk. I'm going to be probably doing another nightly night where I dive into another nightly feature in Rust. I haven't decided on which feature yet, but when I have decided, I'll post the topic to the Meetup event, and you can decide if you want to join or not. But yeah, that's it for today. Thank you all for watching, and take care.
Thank you very much. Bye bye.
Have a good night.
Thank you.
Bye.
All right, bye.